My name is Nat Lifton, and I'm a geologist in the Earth, Atmospheric, and Planetary Sciences and the Physics and Astronomy departments at Purdue. I've always been drawn to scientific technology, but it's the scale of Earth's processes that fascinate me. In fact, I can tell you the instant that I decided to become a geologist. I was on a field trip to the San Andreas Fault, which ran down a deep canyon in the mountains north of Los Angeles. And as I was standing on one side of the canyon, I was visualizing that I was standing on one tectonic plate, looking at another tectonic plate on the other side of the fault, on the other side of the canyon. And the scale of that visualization just completely blew my mind. So I feel like I'm so lucky to be able to have the intellectual freedom to pursue the types of things that interest me, such as being able to ask and to try and answer the questions about how the world works, about how the processes at the Earth's surface work. It's just so much fun for me that my job doesn't even seem like work. So I study ways of figuring out how long rock or sediment has been exposed at or near the Earth's surface, and how fast various processes work that act to shape the landscape around us. I do this using certain rare atoms that are produced in the minerals within the rock or sediment by high-energy cosmic rays from space, if you can believe that, so kind of nuclear physics. These can only penetrate into the top meter or two of the Earth's surface, so if we know how quickly these atoms are produced in a rock or mineral that it's been exposed at the surface, then we can say something about its history at or near the surface. So one of the rare atoms that are known as cosmogenic nuclides is what I work with, and that atom is carbon-14. So it's produced in rocks from oxygen atoms by cosmic rays, different from the organic carbon-14 that's better known as a dating tool. So a number of these cosmogenic nuclides are either stable, in other words not radioactive, or are radioactive but decay very slowly, so on the order of hundreds of thousands to millions of years. Carbon-14, on the other hand, decays much more rapidly, so on the order of thousands of years. And comparing the amounts of these long-lived nuclides with the amount of carbon-14 in a rock allows one to determine whether a sample has been continuously exposed or buried and re-exposed, etc. So I've applied this in Arctic Canada and in other glacial environments to study the advance and retreat of glaciers in particular, which can act to shield the underlying rock from cosmic rays. So this allows carbon-14 in the rock to decay while the levels of the longer-lived radionuclides don't change very much. So that allows us to say something then about the history of burial or exposure of the rock. So climate change is nothing new on the Earth. In fact, it's been varying throughout Earth's history. The aspect of climate that is new is that the rate that it's changing now is unprecedented, and it's going to challenge life on the planet to adapt in ways and with speeds that we haven't had to since we've been here as Homo sapiens. Now, ecosystems have evolved under very slowly changing conditions over many millions of years, which allow for adaptation or migration as climate changes. So the environment and organisms it supports have evolved together in a finely tuned balance as a result of that, because it has the time to do it. The CO2 that we're putting into the atmosphere and oceans since the Industrial Revolution has been sequestered in the Earth for many millions of years, but we're burning through it in an instant of Earth's time span. And this threatens the balance between the ecosystems and their environments.